Okay. Anybody have any vectors questions? Yeah.
I was wondering about number 16, part A.
Okay. Do you happen to have it with you? I could look it up if you don't, but.
I like your sweater. Honestly, though, like, even though this really like.
Okay.
She explained it so much better.
So vectors number 16. Actually, this is kind of related to the stuff that I was going to start with today. So you have this funny shaped object, and you're told that the center of mass here somewhere is the origin, I think. And you have a cable that makes an angle of 45 degrees with the horizontal or the vertical. And it's 1/2 meter long. And it connects to the wall. And then you have a pin down here. And you know that this point is, okay, so the center of mass is the origin. The point where the cable connects is 0.6, 0.4. The point where the pin connects with the body is 0.05, -0.2. And then you have to answer a bunch of stuff. So first, if there's a cable tension T, what's the force vector that the cable applies to the body? And then what's the vector from the pin to where the cable contacts the wall? Okay. So for the first part, you're going to use a unit vector. And there's a couple of ways you can calculate this unit vector. I'm actually just going to talk about this right after. So when I talk about it, you can relate it to this. You can either figure out the coordinates of that point where it connects to the wall, and then just subtract the coordinates, okay, to get a direction. Or you can imagine the coordinate system at the start of your vector, like at the tail of your vector, and calculate the coordinates of the head of your vector, okay? Either one of those will work fine. Let's do that. So let's think of the force vector we know is going to be in this direction, right? Because cables always pull away from objects. And so let's imagine a coordinate system located there, okay? And just calculate the coordinates of the head of the vector. So for part A, there's our coordinate system. Our vector has a length of 0.5, and this angle is 45 degrees. And so that's, well, in this case, we're just looking for the unit vector, so we don't really need that 0.5, but that vector is going to be 0.5 times the cosine of 45 degrees, 0.5 times the sine of 45 degrees, which is like 0.3535. Why am I using so many significant figures all of a sudden? I don't know. So that's the full vector, but we want the unit vector. So now you could take a unit vector of that, but what you would get is just, you know, when you use cosine and sine, that's giving you a unit vector. So if this vector is this, the unit vector in that direction is just going to be cosine of 45, sine of 45. So like 0.7071, 0.7071. Okay, so that's the unit vector in the direction of that arrow. Then now, what's the benefit of coming up with the unit vector? Well, now we know that if we want a vector that has a magnitude of t that's in that direction, this has a magnitude of 1, so we can just multiply it by t, and we get a vector in that direction with a magnitude of t. Okay, so our force vector then is just going to be 0.7071 t, 0.7071 t. And we're going to use that approach all the time. Okay. Okay, so for the second one, for the second part, we want the vector from, no one asked me about that, but this is the one you asked me about. We want a vector that goes from the pin to where the cable contacts the wall. Okay, we have the coordinates where the cable connects to the body, but not where the cable connects to the wall. But notice that if we could come up with the coordinates where the cable contacts the wall, then we could just do the subtraction. Okay, so how do we come up with the coordinates where the cable connects to the wall? Well, notice that the coordinates of the point where the cable connects to the body are really that vector. You know, the coordinates are the components of that vector. And so the components of the vector from the origin to where the cable contacts the wall is just the sum of these two vectors. You see that? I sort of made these look like they're in a line. They're not exactly, but if you want this, let me use a different color. If you want this blue vector components, that's the same thing as the red vector plus the black vector. Okay. Well, the black vector is what we came up with here. That's u. Okay. And so the coordinates at the wall contact are just 0.6, 0.4. Plus 0.3535, 0.3535. And so you get 0.9535, 0.7535. Okay, so now we have the coordinates at the wall contact, and now we can just subtract to get the vector. We want the vector, the blue one. No, we don't. We want the vector that goes from the pin down here to there. So we want this gray vector. Okay. And so to do that, we're going to just go the destination point minus the starting point and you get 0.9035 and then 0.9535. And that's the gray vector. Okay. So getting used to this idea of just thinking of coordinates as vectors from the origin and using vector addition and vector subtraction to figure out vectors, that's going to be like a helpful thing in this class. You want to get used to doing that. Anybody have any questions about that problem? Yeah.
So for part A, it doesn't matter where it's attached the cable.
Well, you could do it that way. I could have calculated the coordinates at the wall contact, okay? And then subtracted the coordinates at the body contact, and then taken the unit vector of that, and I would have gotten the same thing. But notice that when you use cosine and sine of an angle, what you're doing is calculating a unit vector. So we just sort of skipped all those steps. Okay, you can do it either way. That's actually exactly what I'm going to talk about next. So trying to be sort of explicit about how to do this. Any other questions about these? Any other vector problems you want to see before I go on to new stuff? Well, it's not really new. It's from the vector review, but I just want to sort of elaborate on it. Okay, so back to the vector review. Okay, so how do you find a vector bless you, from a point A to a point B? Okay, so these points, when we think of points, we're thinking of coordinates, but you can also think of them as vector components, and the vector is from the origin to the point. So coordinates really are vectors. They're just vectors from the origin to the point, okay? There are two ways to do it. And this is like which one you use is based on whether you know the coordinates of the 2 points or not. If you do already have the coordinates of the 2 points, you just subtract the coordinates. You know, you're just calculating a vector from one to the other one. So if you already know the coordinates of both, then you just subtract the destination point minus the starting point. if you don't already have the coordinates, well, you could just calculate the coordinates and then do it like A, or you can imagine the coordinate system at the starting point, A, and calculate the coordinates in that coordinate system of B. And that gives you a vector that goes from A to B. Okay, well, notice that we use this B approach in this problem, in the first part of this problem. So to calculate that black vector that goes from the contact with the body to the contact with the wall, we imagine the coordinate system at the starting point, the contact with the body, and then we just calculated the coordinates of where it contacts with the wall. That's what this calculation was, the 0.5 cosine of 45, 0.5 sine of 45. Okay? So now the next question is, how do we calculate a unit vector in a given direction? For this, there's two approaches. The first one is if you're given an angle between the vector you want and some reference line. And I want you to remember this. This really is only useful in 2D. So then the way that you're going to do that is just find the counterclockwise angle from the positive x-axis, and that unit vector is going to be cosine of that angle, sine of that angle. And that's all you have to do. I want to show you one example of how to do a problem. These can be really confusing problems, but if you're systematic about it, it's really not that hard to do. So like here's the kind of thing that you'll be seeing eventually. So let's say that we have a wall that makes an angle of 20 degrees with the horizontal, okay? And then we have a slot and let's say the object that we're analyzing can slide in that slot. And we know that the angle between the slot and the wall, so let's say this angle is 15 degrees. And the vector we want by the way, the reason we would want this is because the force vector that slot applies to the object would have to be perpendicular to that slot. We'll talk about that later. You know, we haven't gotten to that stuff yet. But let's say that this is the vector that we want. Okay. So we want to know what the unit vector is in that direction. Okay, that's pretty complicated. Right? I mean, but if you just keep thinking of bouncing around from angle to angle, it's really easy to do this. Okay, I'm going to try to keep bringing this up, but okay, so let's think through this. So here's our coordinate system. Okay. Well, the first thing we know is compared to our coordinate system, this 20-degree angle tells us the direction of either of, you know, any line. There are two vectors that are parallel to that line. We can choose either one of those. I'll show you what I mean as we go, but let's choose, let's do, so our first vector is going to be this one parallel to the wall, okay? So I'm choosing that because we know that the angle between the horizontal and the wall is 20 degrees. We're given that, okay? Now, what's the next thing we know? We know that this slot makes an angle of 15 degrees with the wall. I'm gonna do this the other way just because I think it makes it a little more clear. So I'm gonna, for the vector with the wall, I'm gonna choose this direction and call that 20 degrees, okay? Because now you can see that that slot makes an angle of 15 degrees with that wall vector. So this is 15 degrees. Are you with me on that? And then the vector we want, F, is perpendicular to that one we just drew. Okay, so how do we come up with the angle from the positive x-axis to this vector that's in the first quadrant? We go, that's a terrible estimate of 20 degrees, by the way, but we go negative 20 degrees. Okay, so our theta that we're looking for is negative 20 degrees. And now we're at this one. Okay. Now we're going clockwise another 15 degrees, so that's also negative, so minus 15. Okay. You with me on that? And now we're going to go counterclockwise 90 degrees from there. So we'll go plus 90. Now we're at the vector we want. And so it's 90 minus 35 is 55 degrees, right? And so the unit vector F is just cosine of 55 sine of 55. You just bounce from vector to vector, adding or subtracting from theta until you get to the one you want. just using what you have as references. We could reference the wall from the horizontal, we could reference the slot from the wall, and then we could reference F from the slot. Okay? Any questions about that? Okay, so this is the first way to figure out a unit vector in a given direction. And remember, this is only 2D. You don't want to try to think through this with angles going off of different planes and stuff, okay? The second thing is based on coordinates of a start and an end point. This one you can use in 2D or 3D. If you're in 3D, this is the one you pretty much have to use. So like, for example, let's say that we have a cable that connects to the wall from some body. Let's say that the coordinates at this point are 5, -6. I'm just doing this in 2D, but it works exactly the same in 3D. The coordinates at this point are 7, -5. Okay, and we want a unit vector in that direction. You can see this obviously would be a unit vector that we would use to calculate the cable force that's on that body. So the way you would do that is you'd go final point, the destination point, minus the starting point. So 2, 1. And then you just calculate the unit vector in that direction. So let's see. The magnitude of this is square root of 5. And so the unit vector in that direction is 1 over square root of 5 times 2, 1, or 2 over root 5, 1 over root 5. Okay? I'm going to write down an example, and I want you to just work through this. So let's do one in 3D. So let's say we have a point we'll call this point 1, 2, -4. And we'll call this point -3, +4, -7. So that would be a cable, for example. And let's say we want the vector going in this direction with a magnitude of t. So find the force direction. find the force vector in the direction of that arrow. But with a magnitude t. Okay, take a few minutes, work through that. Feel free to talk to each other or ask me questions if you get stuck. Oops. Okay. So a vector in that direction that's not a unit vector would be -3, 4, -7. The destination point minus the starting point, 1, 2, -4. And so that is -4, 2, -3. I'll call that the vector D. And then the unit vector, well, the magnitude of this vector is 4 squared plus 2 squared plus 3 squared square root, 25, so square root of 29. And so then the unit vector is -4 over root 29, 2 over root 29, -3 over root 29. And so then the force vector is, did anyone get decimals for this? Can you tell me what these decimals are? No? Okay. Well, I'll just write it like this. So -4 over root 29 times t, 2 over root 29 times t, and -3 over root 29. And that's the force vector.
Do you still want the decimals?
Nah. But it was good practice. It made you a better person doing it. Any questions about that? Okay, let's do one of those 2D examples. So let's say it's 15 degrees from the horizontal to this line. It's 40 degrees from the first line to the second line. And then the line we want is perpendicular to the second line. Okay. So give a force vector, and I guess I'll draw this as a vector like that. So give the force vector with a magnitude of capital N in the direction of that arrow. So there are always multiple ways to think about these, but I'm going to think about this first one. Remember, this is like an SAT type thing. I forget what they call these, opposite angles or something like that, vertical angles. This is also 15 degrees. Is that what I'm going to do? Yes. So here's my coordinate system. And the first vector is this way, and this angle is 15. And then from that one, this angle is 40. So that's that double angle mark. It goes all the way from the vector in the first quadrant to this second vector. And then the third one is like this, and those are 90 degrees apart. So I'm going to first, I'm going to think of this as vector A, vector B, and vector C, okay? And I'm going to, from the positive x-axis to get to vector A, is counterclockwise 15 degrees, so that's positive 15. Then from A to B is clockwise 40, so that's minus 40. And then from B to C is clockwise 90, so that's minus 90. And so that's minus 130 plus 15 is minus 115. And so the unit vector is cosine and sine of negative 115. Can someone tell me what those decimals are?
Cosine is negative 0.423. Sine is negative
906. Okay. Makes sense. You can see that the one I drew should have a bigger y component, smaller x component, both negative. And so once we have that unit vector, the force vector is this times the magnitude, which usually in our problems is going to start out as a variable, so we're going to write it as capital N, and then we'll calculate what that N is using Newton's laws. So negative 0.423, negative 0.906, multiply both by N. Okay? Let's see, 6 minutes. I am going to, no, let's just stop there. So I'll give you the rest of the vector problems as the homework, and then we'll get into real statics on Monday. Okay.